Hey everyone, on this lesson we are going to study the conditional dilation and also the reconstruction. So we are now at this point, we will study both of them because they are very connected concepts. And we will see that to reconstruct an image, we will apply many times the conditional dilation. So let's start explaining and studying what is the conditional dilation. So this is nothing more than a operation that we can apply to an image with the help of another image and obtain a new resulting image. So to perform the conditional dilation, we need an input image that we will call the markers image. We will explain this in a bit. We also need a conditioning image and the structuring element. So remember, the structuring element is nothing more than the shape of the dilation, right? So as we can see here, we have this markers image. So we are basically specifying where, okay, of the conditioning image we will going to pick. And then we can apply the dilation operation. So we get this dilated image. As we see, if we dilate each pixel of each white point that we see on this image, we can get bigger and more expanded pixels. Okay, this is the concept of dilation, and we get this image. Now, what is the resulting image of the conditional dilation? Well, the result is given by the intersection between the dilated input image and the conditioning image. So we need to intersect this dilated image that we see with this conditioning image. So at the end we have this resulting image. So as we can see here, the conditioning image is nothing more than an image that has a set of numbers, right? So here we are specifying which numbers we are going to take from this image. So in this case, we are going to take the one that is on the middle, the one that is on top of the middle, the one that is on the left, so on, the ones that are on the diagonal, okay? So here we specify where we will pick those pixels. So we intersect this dilated image with this conditioning image and we get this resulting image. For instance, this one is corresponded to the one in the middle, okay? And then we have the right one, which is this point. Then the top one, which is this point. Then we have this one on the top right, which is this point that we have. So we basically intersect both images. So this is the conditional dilation. So let's see an example of conditional dilation before going into the reconstruction. So to apply this conditional dilation, we have this image, which is the set of cells. This is a old image that we are going to erase. This is the image that we used on the previous lesson, if you remember, on the distance transform. So we are going to delete. And the only image that we need for now is this one, the set of cells. You can download this image on the downloadable documents of this lesson. So let's define the original image, which is the imread of the set of cells .tif. And we are going to plot this image. And let's title this the original image. So let's see how is this image first. And we see that this is the original image, which is nothing more than a set of many cells that we can see. So let's now specify the markers image. So let's specify now the markers image, okay, from this image. So let's define that initially the marker is going to be equal to the image, right? And then let's define that, for instance, all the pixels from the row 2 until the row n-1, and the same for the columns from the column 2 until the column n-1, we are going to set all those pixels to be black. So in that sense, we are only going to get the borders of the cell. So to visualize this markers image, let's plot in a new figure this new image, which is the markers image, and let's title this to be the markers image, right? So let's run this and let's see how is this markers image. So as we can see, we have here the markers image, okay, that we will use to apply the conditional dilation. Very well. So let's define a structural element to be, for instance, a structuring element of the shape of a disk. You can choose here many arguments. We will use a shape of disk since the cells have the shape of circular form. and we will choose radius 1. So this is a disk shape structuring element, right, with radius equal to 1, right? So now let's dilate this image and let's apply the conditional dilation. So the conditional dilation, as we have explained, is the intersection between the dilated input image and the conditioning image. So first of all, we need to dilate the marker's image. So let's dilate it in this line. The dilated image is the imDilate function, remember, with the markers, with the structuring element SC. Okay, so here we have the dilated image. This is the input dilated image. And now let's apply this intersection. So let's define out the conditional dilation image to be the intersection, and this is very important, between the dilated input image, what we already have, and the conditioning image. In this case, the conditioning image is the image IM that we define at the beginning. So here the intersection is basically between the dilated input image, which is the markers dilated, intersection with the original conditioning image, which is this one. This is the conditioning image, and this is the we can also plot, okay, let's plot before, let's comment, and let's in a new figure show this dilated image. So this is the dilated image, dilated input image. So let's put it here. Okay, we run, and we have here the dilated input image. So the conditional dilation, it is the intersection between this image, the dilated input image, and the original image, which is the conditioning image. Okay, so now let's define it here. We press run, and also let's display this dilated and the conditional dilation. So let's put here conditional dilation, and let's title here conditional dilation. So let's run this, and here we have the conditional dilation. Now, why is this called conditional dilation? Well, because we have only dilated, okay, those cells that were on the markers, right? So we impose a condition, and we are going to say, hey, only pick me those cells that touch the markers, okay? So we pick those cells, in this case, and we apply the dilated image, and we have the conditional dilation. Now, something that is very, very important is that if we keep applying the conditional dilation over and over, and so on, that's where we get to the reconstruction. So that's why we explained first the conditional dilation, because now to understand the reconstruction is this basically applying a number of times the conditional dilation. So what is reconstruction? Well, reconstruction is nothing more than applying n conditional dilations until a stable image is reached. To do this, we also need a entry image and image of branch, also called markers image, and the structuring element. So let's see how we can apply reconstruction now and why reconstruction is important. Consider this original image that we have, a set of biological cells, and we want to study them. For instance, consider the situation that you are asked to say what is the total area or surface, okay, that these cells have. Well, here you have a problem. Which one? Well, the cells that are on the border of this picture, you do not know if they are big, if they are small, so you cannot quantify the area of that cells. So you do not have to count them. You have to erase all the cells that touch the border. So basically, all the cells that you do not have the information of the area, you need to remove them for your study and for your analysis, right? So this is a problem that we can solve using reconstruction. First of all, we define a markers image to only get the cells that are on the border, okay? And we have the conditional dilation. So let's continue to apply conditional dilations over and over and see what happens. So now again, we define the conditional dilation in here to be again the new dilation of the previous dilation that we had, so the conditional dilation with the structuring element SC, so on, with the intersection of the original image, which is the conditioning image, right? So we make this intersection, as we see here, over and over. So let's rename the conditional dilation to be smaller, for instance, con D. Okay, so it is smaller and we can write over and over. So here we have the conditional dilation to be named con D. And in the same way here we define this to be con D, and here again con D. So with this line we dilate again, and we apply again the conditional dilation, which is the intersection of the dilated marker's image and the conditioning image, right? So in our case, the dilated input image is the previous conditional that we had. So we keep doing this over and over. Okay, let's do it again and again. For instance, 5 times, a total of 5 times, we're going to apply the conditional dilation. And finally, let's plot this new image, con D, and let's title this image to be N conditional dilation. So we apply many times the conditional dilations. So let's see how is this image. So let's run. So as we can see, we have here the resulting image after applying N conditional dilation. So as we can see, we're basically dilating those cells that were on the border. So in the reconstruction, it is basically this. We apply many times the conditional dilation until these cells that we are analyzing touch and are full reconstructed. So to apply reconstruction or to make a reconstruction, you do not need to do this over and over. There's an easy way in MATLAB, and this is how the predefined function is implemented. And in MATLAB, there's a predefined function with the name of inReconstruct that if you pass the marker image, which is in our case the mark, okay, this is the marker's image, and the original image, the conditioning image, we reconstruct the external cells. So keep in mind that the reconstruction is an infinite sequence of conditional dilations. So now let's plot, figure, and show the reconstructed image, and let's title this the reconstructed image. So let's run. And what do we obtain? Well, we obtain all those cells that were on the border. So as we see here, if we compare the original image with the reconstructed image, right? Here we have on the right all the cells that touch the border. So we have all the cells that we do not want to analyze. Those are the ones that we need to extract and to remove from the set of analysis and the set of study. So how can we do this? Well, once we have the reconstructed image that has the information of all those cells that we want to remove, we can simply subtract the original image minus the reconstructed image, right? So we are going to take all those out of the image. So let's apply this. We can do this with the imSubtract function. So the result image is going to be the imSubtract function. And we are going to subtract from the original image the reconstructed image. So now in a new figure, let's show this resulting image. And here it is basically the cells that we want to analyze. Okay, so what basically it's going to be all the cells that do not touch the borders. So let's verify this. And here we have effectively all those cells that do not touch the border, as we can see. Okay, from the original image, we had some cells that they were on the border, so we do not know the area and the surface of those cells. So now we have erased them, and now we only study the ones that we know for sure the area that they have. So as we can see, the reconstruction operation has many applications. Okay, we only saw one of them, but there are many more and many things that you can do with the reconstruction. And to understand reconstruction, we need to first understand the conditional dilation. So with this, we end this lesson. We remind that you can download all the code that we have used on this lesson, as well as the image on the downloadable documents of this lesson.